It's a pleasure for me to give this seminar to present some of the recent results obtained with mostly with ALMA in the field of planet formation. So yeah, I definitely think that this is a golden age of planet formation, because for the first time in history we have really detailed information on the internal structure of planet forming disks. This is brief the outline of my talk. I will try to give a very general introduction, just to make everyone comfortable of what I will talk about. For some of you, for the experts, it will be a repetition, but that's fine. Then I will show some observations, ALMA observations of protoplanetary disks. We'll talk about a specific topic this is essentially the dust rings, the origin and evolution of dust rings. If I have time, I will also talk a little bit about spiral structures and we'll conclude with some conclusions. So, as we are really in the golden age of planet formation, first of all, because of the discovery of exoplanets. As you all know, we are now counting more than 4,000 exoplanets around the stars of different spectral type. And if what we are think we are learning is that planet formation is a common process in the galaxy, but at the same time that planetary architecture, the structure of planetary systems is highly heterogeneous. This, as an example, this diagram shows the distribution of exoplanets detected with different methodologies. On the x-axis, you see the orbital distance of the planet. On the y-axis, the planetary mass. And as you see, essentially, all the plane is essentially is full of dots. The only region that so far is not covered is the planet on wide orbits and a low planetary mass. But this is an observational bias. So why we want to study, why it's important to study protoplanetary disks? The first reason, I think, is because they provide the initial conditions, the initial physical conditions, essentially the mass, temperature, ionization, which are ingredients for any kind of planet formation theory. In particular, the two main scenarios for the formation of giant planets. I will mostly talk about giant planets. There's the core accretion model, that is the standard model, and the gravitational instability. Now, very briefly, the core accretion is a multi-step process. It starts from the coagulation of dust grains. Dust essentially reach the disk from the ISM with the property of the ISM, so it's micron-sized particles. So they have to grow in size and form centimeter-sized bodies and pebbles, and then for collisions form planetesimals, and finally, and eventually, the rocky core of planets. Core accretion, the drawback is that is in a standard setup is a slow process. It takes millions of years to form giant planet, and if you remember the diagram before, it has some problems to form giant planets on very wide orbits, and we know that these planets exist. On the other hand, the alternative scenario is the gravitational instability. We essentially, if you want a number, a way to discern whether a disk is gravitational unstable or not, what we usually look at is the tumor parameter Q, which is essentially proportional to the disk temperature and rotational velocity, and if this number is low, is usually below 1, you may have an unstable disk. What is important here is that at the denominator of Q is the surface density, which is the mass. And from here, you already see that GI, gravitational instability, is efficient only in the cold, because of temperature, outer region, because of the low rotational velocity, and only for massive disks. Okay. At the same time, protoplanetary disks offer the opportunity to study the chemical enrichment during the overall formation of stars and planets. At the end, we want to know where the big molecules, the molecules that allowed the biological evolution of our planet, where did they form, and what's the role of disks in this evolution of chemistry. An important topic, modern topic about the chemical evolution is, in particular, we want to understand what is the role of disks in the chemistry. Whether chemistry is totally reset during the formation and evolution of protoplanetary disks. And hence the planetary composition is essentially is a logical evolution of the chemistry in the disks, or whether disks just inherit the chemical evolution of the prestellar phases, and by consequence also the planets inherit the chemical composition. Now, if on one end we have the large discovery of exoplanets, on the other hand, the last years were very fruitful because of new instrumentation, and particularly ALMA, and I will mainly talk about ALMA today. So for the few of you, I know that maybe not know what ALMA is, as the largest array interferometer working in the sub-millimeter range, and thanks to this superb angular resolution that allow us to reach scales down to a few astronomical units at the nearest star forming region, and also to the sensitivity, which essentially for the first time again we can map the spatial distribution of different molecular species, in particular the rare isotopologues and even the large molecules. Then these two capabilities of ALMA are really revolutionizing the field of planet formation. So I need to talk a little bit about what we think we know about the internal structure of protoplanetary disk. The major heating source is the central star, and by consequence, because of the density gradient in the disk, we usually assume that the disk is vertically is a layered structure with the outermost layer, which is similar to a PDR photodissociation region, where the atomic lines are emitted. Deeper into the disk, the UV radiation is shielded, and the moderate temperature and density allow the formation of a rich molecular layer. More deeper in the disk, close to the disk midplane, the temperature is low, is below 100 Kelvin, and here is where most molecules are condensed on ices, and where all the evolution of dust occurs. The dust grows inside and settle to the midplane, and then can migrate and form the seed for planets. So before ALMA, our view of protoplanetary disks was pretty limited, most of the analysis was done on the ACD, and the most advanced images that we had 10 years ago, for example, with the SMA or the Karma submillimeter arrays, provided us very limited information. Essentially, all the disks looked like having a very smooth surface density distribution, and only in some cases there was we knew that there was a sort of inner dust cavity, and these disks were, we thought that these were called them transitional disks because they were thought to be in a transition phase between the gas-rich primordial phase and the gas-poor debris phases. But most of this observation provided very limited information, and this was I guess you all know this object, HL tau. This was one of the most detailed observation of a class 1 disk, essentially of a young disk obtained with Karma in 2011. So this is for some reason is also the perfect shape to fit, because you can fit any model here. So you don't learn really much. But then, as you know, ALMA came in, and this beautiful image was quite impressive, because what you see here, this is the dust continuum. I forgot to say, also in the previous image was the dust thermal emission, the cold dust, which is a temperature of nearly 10 Kelvin. So where you see the color is it means there is dust. Where you see the black rings is a signature of lower dust density. So you see that there is a lot of substructures. The dust is focused in sort of rings. And now we have, thanks to other different groups, observed that at a very high resolution. These are the other ALMA images of dust continuum and different objects. Here's just a random collection, and what you see here is that dust rings and gaps are very common. This was a big surprise, because we expected all these disks to be still in the phase of forming planets. What we are learning here is that the disks are instead dynamically evolved, and apart from the rings and gaps, which are by far the most common structure, we also see some azimuthal asymmetries. More objects observed at a high resolution. This is the result of the D-sharp large ALMA survey by Shona, Andrews and collaborators, and it's beautiful. This you see that, as I was saying before, disks are highly substructured. So by not at all smooth structure as we thought until 10 years ago. Okay, but what is the origin of rings and gaps and cavities in disks? This is the first question I would like to ask and follow you, and I will guide you for some what we are learning in the last years. So there are different ways to form actually dust gaps and rings. The most popular one, of course, is the dynamical interaction with planets. But this is not the only one. Is not the only process. Actually, there are many ways. Here I list some of just some of them. The formation of dead zone by magnetorotation instability can also produce can also pile up the dust in rings, and You see an example in a model by Mario Floch in the diagram on the left, but also because of the temperature gradient in the disk is characterized by condensation front or snow lines. What happens is that at every condensation front, there is a phase transition. The molecule freeze on ice, and locally what we have is an enhancement of the solid component, and this can also trigger a trap for dust and piling up dust at some specific locations. This is the panel C on the middle. But also photoevaporation can produce cavities and rings. And last but not least is also even MHD winds are very efficient, especially in the very early phases, to form many dust rings. But most of these models, essentially, although they are very efficient in forming dust caps, most of them, or essentially all of them, but one, they fail to produce gas substructure. What the results that I showed before were essentially based on dust continuum observations. Now we have a number of evidence that, at least in some cases, this peculiar structure of gaps and rings is produced by giant planets. And we have, this is my opinion, we have three main evidence. The first, of course, is a direct detection. And this is the case of the object PDS 70, where the dust is as a peculiar characteristic ring structure with a large inner cavity, and two planets were detected directly. But the direct detection is so far there are very few, if less than a handful of objects with a detection or a candidate detection. But there are two ways to infer the presence of protoplanets, in particular giant protoplanets, and both of them rely on looking at the perturbation induced by the planet on the gas surface density or on the dynamics. It's the case of I will talk here most about the gas surface density perturbation, but it's also it's also very interesting to see what is coming out of ALMA observations of spectrally resolved CO images, where we see that at the location of where we expect that there is where we see that there is a dust gap, there is a deviation from Kuiperyan rotation of the gas, and this is thought to be to be produced by the dynamical perturbation of the planet. So how can giant planets open a gap? This is a well-known theory before ALMA came in. Essentially, we know that a giant planet perturbed the gas surface density distribution, pushing away the gas from the orbit of the planet, and locally the pressure gradient is inverted, and by consequence the dust piles up at the resonance location. We also know that depending the gap properties, essentially the depth and the width of the gas gap are dependent on the planetary mass, and this is what you see here is a simulation by Willie Clay that shows how the depending how massive is the planet that you put into the disk, the surface density distribution is perturbed very easily. The more massive the planet is, the deeper is the gap. The deeper and the wider is the gap. Now, we need here a tracer of the gas surface density, and this is not an obvious question because many gas tracers in the disk are sensitive to the temperature gradient, to the density gradient. They can be chemically active. But a robust method is to use contemporary observation of multiple CO isotopologues, and this is because of the intrinsic different abundance of the CO isotopologues. What happens into the disk is that the most abundant isotopologues, 12CO and 30CO, 13CO, they trace the uppermost layers of the disk. When you go to rarer isotopologues like the C18O, the lines, the transition starts to be optically thinner, not fully optically thin, but they are thinner. Tau is lower, and as a consequence, the different isotopologues essentially they trace different layers, different vertical layers, and a combination of them is very useful to look at local surface density perturbation. And this nice paper by Stefano Facchini, they show how the CO surface density is affected by the presence of the planet. Here, the planet is always at 20 AU, is a fixed position, and by changing the mass of the planet, you see that the gap becomes the perturbation that you see by studying the CO surface density becomes deeper and wider. Okay, so I looked at one specific object, which is HD 169142. Is a star of around 2 solar masses, relatively old for its classes. At the age, there are big errors, but it's somewhere between 5 and 10 million years. What you see here is a beautiful images of the dust continuum, where you see a beautiful double ring structure. And when we look at the gas lines, what we also see is that by looking at different transition, here is the 13CO, the 221, and the C18O. You don't see a smooth surface density, a smooth surface brightness, sorry, but it also looks like ring-like structures. And what is also interesting to see here is that the different molecules, the 13CO and C18O in this case, the emission peaks at different location in the disk, and this is because of the intrinsic nature. The 13CO is more, being optically thicker, is more sensitive to the hot dust temperature in the inner disk. C18O, that is thinner, is more sensitive to the total surface density. So this is just a radial profile of different tracer. In black, you see the dust continuum with the two main structure: an inner cavity inside of 20 AU and a dust gap between more or less 30 and 60 AU. You see that the gas, in this case is C18O, does something similar, but not exactly. So it is depleted in the very inner part, but then there's a plateau, and then it peaks farther out in the disk. It's also interesting to look at the small dust grains here traced by observation with sphere, the BLT, and is the curve in the green curve. It shows some similarities here. There's a lot to say here. What is interesting is that how the large dust grains traced by the ALMA continuum are very localized. You see these two main rings, while the gas and the small grains instead are much more extended, and as you see, they seem to go together. And this is what we expect, that the small grains, the micron-sized grains, are dynamically coupled to the gas. So to go from observations to surface density distribution, I used the DALI thermochemical code. Okay, you start from observation. You as an input, you provide the surface density distribution as a parameterized surface density distribution, and some other physical parameters. And with the code, compute the continuum relative transfer. Then you can also do the chemistry. So depending on how accurate is your chemical network, the code compute the molecular abundances. With the initial continuum radiative transfer, the code compute the excitation. Then the next step is the thermal balance, which is used to which gives us as output the gas temperature, and after a few iterations, we reach a convergence. Then the retracing, and the output is the spectral lines, spectral cubes, and the dust maps. If these are fine, okay, you write the paper. If they are not fine, you go back and reiterate, changing the input structure. In this case, we built what we see is that this on the left you see it's a sort of forward modeling. What you see is on the left is the surface density distribution that fits quite well the observation of dust and gas. And in particular, what we concluded that is the dust ring, the dust as expected is confined in two main rings. The gas is also perturbed. It's not a smooth distribution, but it has this peculiar shape. Okay, the question here now is how is this structure possible? The two main dust rings are stable or are they short-lived? And the other important question is the CO surface density distribution consistent with the presence of giant planets? To do this, we performed other dynamical simulations with the Phantom SPH code by Price and collaborators. This is a very nice work by Claudia Tocci. What you see on the left is the actual aerodynamical simulation for the dust and the gas. Time here is evolving, and you see that. So we injected arbitrarily two planets. The planets are free to migrate and accrete mass. And the curve that you see on the right panel is the temporal evolution of the surface density of dust on the top and gas on the lower panel. The curves from blue to red is the temporal evolution. Blue is the early phases, red is the later phases. The final interesting result is that so the two planets are produce consistent dust and gas surface density structure. So what we have learned with this object and the analysis of HD 169142 is that the two giant planets are indeed required to produce the gas and dust distribution that we see with ALMA. We also learned as bonus that the dust rings in this object are actually long-lived, and this is of a peculiar. This is exactly because the planets are in a particular configurations. We also, what the SPH simulations also suggest us, that the planets migrate until they reach a stable resonance. Of course, we don't know what will happen afterwards, but once the disk is dispersed, and also a consequence of the presence of the two planets, that the inner planet stops the further accretion towards the star and depletes the inner disk very, very quickly. It is so we know. Okay, we inferred the possible presence of two giant protoplanets in this object, but the direct detection was still missing until paper by Raffaele Grazzone and collaborators in Padova. They look back at some archival VLT sphere observations, and they highlighted the presence of a possible candidate at nearly 40 AU. You see here with the letter D with a green circle, which is in a very interesting location because it's exactly between the two dust rings. Now it's important, okay, as a follow-up program, okay, we asked ourselves, okay, are all dust rings that we observe with ALMA are stable in time or not? Here I'm going to show two hydro simulations, again based on the Phantom SPH code. On the left is the same object, is 169142, gas and dust respectively. On the right is a simulation for another object, PDS-70, with the one where the two planets were detected with NACO and Sphere. So from a physical point of view, the two disks are in principle similar structures, but the planets are in a slightly different locations. So I let the simulation goes, and what you see is that while in the left case the planets will stop migrating where they reach 5-to-1 resonance, and the rings, the intra-ring, the intra-orbit ring remains stable. In the other case, on the right for PDS-70, the mutual interaction of the two planets with the disk are destructive, and the rings is totally destroyed. So this is also interesting in the perspective of the other ALMA observations. Okay, now we have, I think, robust evidence that the sum of the dust gaps that we see every day with ALMA are produced by giant planets. Important question here is: are there planets in every dust gap? Because if you remember, for example, the image of HL Tau, it was very rich in dust rings and gaps. So for this, I'm gonna talk about a little bit AS209, which is another Clement sequence star. In this case, it's a solar mass star, so much younger. The age is should be something between 0.5 and 1 million year. The dust continuum shown here is a beautiful collection of rings, and let me steal the title by the Tolkien opera, The Lord of the Rings, because this is really the Lord of the Rings, and as I will show later. On the right, you see the radial profile of the dust continuum. At this resolution, this is what we see. This is a major gap at 100 AU, but there are also other structure inward. A few months later, published this. There were the result of the D-sharp D-sharp ALMA survey came in, and this is the same object, but just at higher angular resolution. And you see that there are rings everywhere. The inner core that we did not resolve is actually made of many dust rings. Okay, but thanks to our moderate spatial resolution, we could also observe the gas, and gas is much more complicated than the dust, as you will know, because the observation is a line observation. It's not a broadband observation, so it takes much more time. But what you see here, that already from the comparison of the 13CO and C18O, you see that while the 13CO has a central blob and then a more or less smooth emission towards the outer disk, the C18O as again the central blob, then there's less emission at some range of radii, and then the line becomes again brighter in the outer disk. Very beautifully, the DCO plus instead, which is a cold gas phase tracer, shows an emission ring which spatially anti-correlate with the C18O. Then, okay, from this observation, it's difficult to see the structure, but when we look at the radial profile again, now this is the radially azimutally averaged radial profile. In black is the continuum, and in red the C18O. Now again, what we see here, as we saw for HD 1669142, the C18O emission is not smooth. It's not a power law, okay, but there is a broad gas gap, which is a signature of the perturbed surface density. Okay, and there is some, and this is also spatially coincident with the dust gap, although there are some differences. I played again with a Dalit thermochemical code. On the top left, you see how I parameterize the gas surface density distribution from playing around with in this case with the depth of the gas gap, and the output is the brightness profiles of the three CO isotopologues. What is very interesting to see here is that while the 12CO and the 13CO don't show much difference, even when the gap is deep in the gas, the effect is seen in the C18O. This is because what I was saying before. This is due to the optical depth of the different lines. Although the model is not perfect, there's no way to match perfectly these observations. The simultaneous fit of the three isotopologues is important because of the vertical temperature gradient to be constrained. Also, in this case, we performed hydrodynamical simulations. In this case, using the Fargo 3D by Benitez, Lambey, and Masset. And what you see here is that two sets of simulations. In one case, the red curves are for one single planet at nearly 100 AU. There's a 0.2 solar mass, Jupiter mass planet. And if you see the red curve just with one single planet what we are seeing here is that the perturbation induced by this planet produce multiple gaps and rings even inward of its orbit. Highlighted here the location of the gaps and the rings in our ALMA observations. And this is interesting to see that with this just one single planet, the hydro simulation predict very well the location of the dust rings and of the gaps. So this, what you see on the left is for a zero turbulence case. On the right is the alpha 10 to minus 4, which is there is some turbulence, although it's still very low, a low number. These simulations kind of suggest that the turbulence in the disk is very low, or there's no turbulence at all. We also played around. Okay, we said, okay, what if there's another planet in the inner gap between 50 and 70 AU? And these are the blue and green curves, where the curves are for different planetary mass. The interesting result is that for the outer rings, nothing really changes apart from the green curve, which is for a more massive planet. The presence of the second planet impact more the internal structure of the disk as expected. But so here, what we have learned from this exercise, that we cannot really distinguish if there's a second planet at 60 AU, but for sure we learned that even one planet at 100 AU is enough to produce the multiple gaps and rings. And again, to refer to cite the Lord of the Rings, here we have one planet to rule them all, so one planet to produce multiple dust rings and gaps. To the same conclusion became also Zhang et al. When they fitted the highest angle observation obtained in the D-sharp survey. In addition, we have the gas profile, and we performed also very high resolution other simulation in the gas. These are a bit more complicated, takes much more time. Now, if you concentrate on the right plot, you see how the effect of the perturbation of the gas surface density produced by a 0.2 and 0.3 Jupiter masses planet, again at 100 AU. These are the same set of simulation for gas and dust. You see they produce different structure as expected. What is important here is that not only the gas, the CATM observations are important to confirm the presence of the planet. They tell us actually even more, because we can constrain even the lower limit of the planetary mass that is needed to produce this gap. And in this case, we expect to have at least something a bit more massive, a 0.3 Jupiter mass planet. Okay, just a few more minutes to talk about spiral structures, because we don't see only rings and gaps, but we also see a lot of spirals. Now, if you remember, the gravitational instability scenario predicts the formation of spiral structures, and this is actually this is a result not coming from ALMA, but actually from SPHERE. And there is now extensive literature of young disks where the near-infrared observations show peculiar structure. Here I'm showing 3 cases from the PhD thesis of Maria Giulia Ubeira Gabellini, where you see all kind of asymmetries in the very inner part of disks. So are this signature of gravitational instability? Well, I don't know the answer yet, but we look at one specific object, HT 100546. Starting from the left is the last continuum observations. Here, this object is very peculiar at ALMA at millimeter wavelengths, because the inner part of the disk is extremely bright and show a compact ring around 20 AU. If you see the image here, the central part is the colors are saturated, because I wanted to show the outer part, because what you see that in the outer ring at nearly 200 AU is not at all a ring. It is a very highly substructured. It looks like it's a fragmented disk. And very interestingly here is also the wide gap between these two structures, the inner ring and the outer ring-like structure. This is rather peculiar. And by zooming into the inner part, this is the object. This is one of the objects that we know that there are a lot of spirals in the inner 50 AU. I'm not sure. I didn't show here, but if this object also has large-scale structures observed with, for example, with the HST already in 2007 by Davide Fedele. So now the presence of spirals in these objects are very are robust, and many authors actually highlighted them. This shows a radial profile of the dust of the ALMA dust surface density. And as I was saying before, it is peculiar because of two main reasons: the large contrast between the inner and the outer ring, and the very wide gap. It's wider than 50 AU. This object is also a protoplanet candidate discovered back in 2013 by Sasha Quans with observation in the L band with NACO. And I would say, I think it's not a candidate. I think it's confirmed. And because there were also follow-up observation in the M band at 5 micron that confirmed the detection of a point-like source. And very interesting, this object should be located between the two dust rings that we observe with ALMA. Okay, what we are doing to understand what is going on in this object, again with Claudia Tocci, we are running phantom SPH simulations. We're interested here more on the outer structure to understand how if there is just one planet, is this able to fragment the disk to produce this wide gap between 50 and 150, between the 50 AU dust gap, and where the planet formed. Now, a problem, but also a result that we encountered with the simulations, that in order for the planet, for the outer planet, to stop in the center of the gap at more or less 100 AU, because of the migration, the planet should have formed initially at very wide orbits, much farther than 100 AU. And what you see here is the evolution of the orbits for different models. And A2 is the final orbit of the planet, of the outer planet. We also in our simulation we also put an inner planet, which is needed to produce the inner cavity. Okay, but for sure, what we are learning here, this is a work in progress. What we are learning here is that the formation of the presence of a massive planet is required to form this large dust gap, but the formation itself should have started very farther away. So to conclude on this very general overview of what we have learned with ALMA in the last years, ALMA and also SPHERE in the last years, that planet formation starts very early on, much earlier than we previously thought. The presence of planets is actually very of giant planets is very important for the dynamical evolution of the disk. We start to see some similarities between the planetary architectures and disks. And going back to the question, how do planets form? I think we can say that the presence of giant planets on wide orbits is consistent with the gravitational instability scenario. And that's all. I think I want just to conclude to saying we are this is the golden age, but the golden age will last longer thanks to a new suite of instrument that is coming, and at infrared wavelengths. Pretty soon we'll have IRIS at the VLT, which is ideal to detect embedded planets in the gap, but we will also have James Webb from space, and on a bit longer time scale the ELT. But at longer wavelengths, even after ALMA, future interferometer, like for example the NGVLA, will provide us very very useful information, because at longer wavelengths the disks are even optically thinner, the emission is optically thinner, and we'll be able to study younger and more massive disks. And with this, thank you for your attention, and